Okay, so a long time ago, an old man said, let's look at x, how far the random variable, the expectation of that, is from the mean. But the thing is, this does not look mathematically pretty. So let's look at the squared. So expectation of x minus mean squared is equal to expectation of x squared minus. Remember, this is a function of the random variable. We can do that. And that is itself a random variable. We can actually say the sum of random variables is actually a random variable. And that requires the Fourier transform, which is very beautiful. And the Fourier is actually central limit theorem. We can see that if you keep on summing the random variables, and even different ones, it's going to approach a Gaussian. It's very nice, very pretty. And you prove that using the Fourier transform. Or you could prove it. You can prove it in many ways. Equals minus 2 mu x plus mu squared, which is equal to, remember, expectation, we use a sum. We have a summation formula, right? Summation is linear in this sense. We can actually split it up. So that is good. So this can be seen as the expectation of x squared minus 2 mu is expectation of x. Remember, we can actually pull out a constant also because linearity uphold, which is good. Minus expectation times x plus x squared expectation of x squared. Remember, mu is equal to the expectation of x, and the expectation of a constant value is a constant value. Just put it out. Very simple. And this is equal to expectation of x squared minus expectation of x squared on the outside. This much easier to work with. It even shows you a relationship with the expectation of x, which I like very much. And this is used in many formulas. So we can actually say there's conditional variance and conditional expectation. And we actually look at we condition the function. And we actually look at the probability of that. We look at the conditional random variable. But let's save that. Now there's something called now let's go on to continuous random variables. So I'm going to ask you a question. There's a dartboard. What is the probability that when I throw the magical mahjong piece, it's going to hit the dartboard? Well, right now it's 0. But if I actually hit it in here, and I'm going to ask you, what's the point? What point did it hit? What's the probability that it's going to hit the mahjong piece? When I throw it, it's going to hit this point. Probability is 0. There's infinitely many outcomes within this circle. Let's just say for ease, this is a unit circle. It's not really, it doesn't look like a circle, but it is a circle. So this can take on, our space is no longer finite. So infinitely many. In fact, it's no longer countable because you can say there's a mapping that this is a real number. The real numbers, any subset of the real numbers is uncountable. So there's no point in trying to enumerate it. Remember last week we did the Cantor's diagonalization argument. So screw it. I'm sorry. Momentai. That's better than saying screw it. So, and for example, I'm gonna go to a bus stop. What is the I go between 5 p.m. and 6 p.m. What's the probability that I arrive at exactly 5 minutes? And I arrive exactly 5:31 and 33.333333 seconds. 0. So we actually need to do some integration in this. And we also need to talk about cumulative distribution function. You see, before we talked about random variables, I can tell you what's the probability with geometric probability. What's the probability that it's going to take more than one time? I say the sum of all everything else. Now everything's more complicated in continuous variables because I can't do that. In fact, if I said what's the probability that it won't be that in the unit circle it won't be at the origin, it's gonna be 1 probability. So it gets a little bit more complicated. It's a continuous PDF. So let's look at a few things. First off, we should start with the simplest one, which is remember the simplest one for discrete is Bernoulli. Simplest one for continuous, simplest model is uniform. So now we're going to look at the continuous function. Let's say that in my outcome experiment, it can be anywhere between A and B. So I go to a bus stop at A, and the bus can arrive anywhere from time A to time B. It can arrive when I get there. It can arrive a few seconds after I get there, but it has to be no later than B, because my universe does not allow it, for I am the ruler of my universe. So, and we say that it has equal chance that it's going to arrive at any spot. That's a very, very big thing to say, big assumption. Not many things can be modeled in uniform continuity, because that's a big assumption. But let's just make that assumption. Then this guy should be like that. But what should be the probability overall of this guy? Well, if I said what's the probability it's going to arrive if I'm going to be here, it's going to be 0. Or here, it's going to be 0. So we're going to look at when we compute the probability, we have to compute it as an integration. So the probability of all these guys, so let's say the integral from A to B of this function, this is called p of x, has equal to 1. Only way this is possible with this module. And they're all equal probability. We're going to end up showing that this guy, when we compute out all the probabilities, we're going to do moving to the side and saying this has to equal to 1. It's going to end up looking at this probability. We can say that the sum of this guy has to be the probability distribution function. Yeah. 1 over b minus a. Right? Very sorry, I have not looked up this stuff up in a year. Yeah. So for between the interval when x is going to equal to 1 over b minus a, and everywhere else, it's not going to be possible anywhere else. So everywhere else, it's going to be 0. Now this doesn't mean that the probability of x is equal to this. It's just a way to say how you assign. So let me give you an example why we need this. Well, actually, let's just say what the function looks like. But the fact is, that's not the probability. A PDF is not the probability at each point. Do not think that. Cumulative distribution function, a little bit different. But in pmf, it's the probability at each one. But these guys, not a probability. I mean, not a, you get my picture. It's actually, so, if I wanted to say what's the probability that arrived between a and a and a plus, let's say, a plus 3. It's going to be integral from a to a plus 3 of f of x dx. Some of these guys will be in between. Some of them will not. This is the probability. That's a uniform distribution. Right there. Okay, what else is there? There is exponential. That's e to the minus lambda. Exponential distribution with lambda. Let's see. Ooh, is it over?